Welcome back, everyone. Before the break, I had started to introduce the idea of a scale factor. In this part of the lesson, we're going to focus on what a scale factor does when I'm calculating the surface area and the volume of three-dimensional shapes. Let's go to the next slide together. So, everyone, I'm first going to remind us that the surface area of a rectangular prism is calculated by adding the areas of all of the rectangles that make up the rectangular prism together. So just a reminder, the surface area, I take the areas of all the shapes that make up the figure and I add them together. Now, because it is a rectangular prism, I have three sets of equal rectangles, and I find the surface area by saying 2 times the length times the breadth plus 2 times the length times the height plus 2 times the base times the height. And then for the volume of a rectangular prism, we take the area of the base, and the base is this particular rectangle. And the area of the base is length times breadth. And for volume, I multiply the area of the base by the perpendicular height. And my perpendicular height is just h. Now, guys, we are going to see what a scale factor will do to the surface area and the volume of a rectangular prism. Let's first have a look. So if I say this particular rectangular prism has a scale factor of 2, this means that the length has been multiplied by 2, the breadth has been multiplied by 2, and the height has been multiplied by 2. I am now going to calculate my new surface area using the fact that this is my surface area formula. So now for subbing in for my length, breadth, and height, I'm going to be subbing in 2 times those distances because my scale factor is 2. My scale factor being 2 means that each side has been multiplied by the scale factor. So each side's been multiplied by 2. So you can see here I've replaced the length, breadth, and height, each with being multiplied by 2. And this simplifies to 8 length breadths plus 8 length times heights plus 8 base times height. But the main thing that I want you to see, what's interesting, is if I look at the difference between my original formula and what the result of multiplying by the scale factor did, we can actually see that it's now 4 times the original formula if I take a highest common factor of 4 out. So I'm going to ask you guys to start seeing if you can see a link between the scale factor and how this relates to how I can express the new surface area of a particular shape. Cool. Let's look at what happens to the volume. Now instead of length times breadth times height, I now have 2 lengths times 2 breadths times 2 heights. And this gives me a result of 8 length times breadth times height. Also, everyone, I'm going to start asking if you see any connections between the relationship of the new volume and the scale factor. So I want you to start looking, is there any connection at all between the scale factor and how I can write the new volume? Let's look at another example with a different scale factor. So the next scale factor that we are going to be looking at is 4. Similarly, we are going to be multiplying the length, the breadth, and the height by 4. And those are going to be substituted in to the formulas where we've got length, breadth, and height present. So again, all I've done is replace all of those distances with 4 times that distance. This simplifies to be 32 lb plus 32 lh plus 32 bh. Again, guys, is there any way that I can express this new surface area in terms of my old surface area? My old surface area is the normal formula, and if I want to try and see what the connection is, if I take out a highest common factor of 16, I can see that the scale factor of 4 led to my surface area being 16 times the original surface area. So again, I'm going to ask you to put your thinking caps on. Is there a link between these two? Similarly, for the volume, I've substituted in the new distances, and I got 64 times the original volume. Is there any link between the scale factor and the new volume? I want you to start thinking. We're going to talk about it just now, but I'm hoping that someone's going to catch it before I say it. Great, let's look at another scale factor. So the next one is a scale factor of a half. So before we continue, just in case the half is throwing you off, it is possible for me to reduce the dimensions. So obviously, I can imagine a box being 2 times larger, but also I can imagine the lengths of a box and the dimensions of a box being half that size. So instead of doubling or tripling or quadrupling the lengths, we are now halving the length, the breadth, and the height. So it is possible to have a fraction as your scale factor. Let's see what it does to the surface area and the volume. So we've now got a half length, half breadth, half height. Again, substituting it into the old formula, and again, trying to see, is there a link between the old expression for surface area and the way that I can write it in terms of the new one? And everyone can hopefully see that if I take a quarter out as a highest common factor, I can see that a quarter times the old surface area is an expression for the new surface area. Again, if I look at the lengths, what is the relationship between a half and a quarter? Well, it is a half squared. And if I look at my previous slide, I'm sure that everyone will agree that I can see that my surface area was affected by the scale factor being squared. So I'm hoping that everyone's starting to see a bit of a pattern, that the scale factor squared can be multiplied by the surface area to get the new surface area. So let's now look at the volume connection. Again, just substituting in the dimensions affected by the scale factor. It's equal to 1/8 times length times breadth times height. I'm going to ask you guys to carry on thinking about the link between the scale factor and the volume question. We're going to discuss this one on the next slide. So for this next one, I've done a very similar process, except now I've substituted in 10. We can see that the scale factor influenced the surface area in a way that it is going to be 100 times the original surface area. So in general, everyone, we can see that the surface area of a 3-dimensional shape, and in this case it is going to be the rectangular prism, the scale factor squared times the old surface area is representative of my new surface area. Let's look at the link between the scale factor and the volume. We can see that 1,000 is actually 10 cubed. And if we look at this connection between the scale factor and the new volume is equal to the scale factor cubed times the old volume. Cool, guys? So in general, we can say that if the length, breadth, and height of a rectangular prism have been multiplied by a scale factor of k, then the surface area will be multiplied by k squared, and the volume will be multiplied by k cubed. Great, everyone. I hope that everyone's with me. We're now going to be going into an example to look at how we can actually calculate surface area and volume using a scale factor. Let's go to the example. So guys, for this question, we have been given a rectangular prism. We are first going to calculate the volume of the particular rectangular prism. Then we're going to calculate the volume of the rectangular prism if the length, height, and breadth are multiplied by a scale factor of 2. For C, we're going to calculate the surface area of the rectangular prism. And then D, we're going to calculate the surface area of the rectangular prism if the length, breadth, and height are multiplied by a scale factor of 3. Let's get going. So we're first going to calculate the volume of this particular rectangular prism. And luckily this is a straight substitution. It's our area of our base, which is length times breadth times our height. Something that can help, you don't have to do this, but it is a recommendation, is what I would do is just write what my length is, what my breadth is, and what my height is for this example, just so when I'm substituting it in, it's fairly clear as to which values go where. So my length is 11, my breadth is 3, and my height is 4. So I'm going to end up having my length times my breadth times my height. And this is going to give me an answer of 132 centimeters cubed. Please remember, it is centimeters cubed because this is a volume. Let's go to B. So it says, calculate the volume of the rectangular prism if the length, height, and breadth are multiplied by a scale factor of 2. So everyone, please remember that this means that now we're going to have 22 centimeters as our length, 6 centimeters as our breadth, and 8 centimeters as our height, because it has been multiplied by a scale factor of 2, which means I am doubling all of my lengths. There are two ways to go about this. You can either say 8 times 22 times 6, because these are your new values for the volume, or we can use the knowledge that we know that the volume of a rectangular prism is k cubed, where k is my scale factor, times length times breadth times height. So my scale factor is 2, so I know 2 cubed times my original volume of my rectangular prism, which if I fetch from the other side, I can see it's 132 centimeters, so I'm going to carry that forward. So it's going to be 2 cubed times 132, because my scale factor influences my volume, as my scale factor cubed times the volume gives me my new volume. So let's pop that into the calculator. So I'm going to have 2 to the power of 3, 2 cubed, multiplied by 132. So my new volume is 1,056 centimeters cubed. Great, everyone. I hope that you're with me so far. Just remember that when I've got a scale factor influencing a rectangular prism, it is going to be the scale factor cubed multiplied by the original volume. Let's go to the next part of the question. So we are now going to calculate the surface area of the particular rectangular prism. Again, I'm just going to write my length is 11, my breadth is 3, and my height is 4. So we again need to take the area of all of the different rectangles that make up this particular prism. So I'm going to have 2 times 11 times 3 plus 2 times my length times my height, which is 4. Then I'm going to have plus 2 times my breadth, which is 3, times my height, which is 4. So I've now substituted in the length, the breadth, and the height to get the area of all of these rectangles. Now I'm going to plug it all into my calculator just so I can get a final answer. So it's going to be 2 times 11 times 3 plus 2 times 11 times 4 plus 2 times 3 times 4. So my surface area is 178 centimeters squared. Just a reminder, because it is the surface area and it's adding the area of the 6 surfaces that make up the rectangular prism, the units are squared. It's only cubed for volume. Let's go to the next part of the question. So we are now going to calculate the surface area of the rectangular prism if the length, height, and breadth are multiplied by a scale factor of 3. Just a reminder what we said, the influence of the scale factor is on the surface area. We said that the scale factor squared multiplied by the surface area will give me the new surface area. So my scale factor squared will be 9 because it's 3 squared, and I'm going to multiply it by my original surface area, which is 178. So I'm going to have 9 times 178 in order to find my new surface area, which is 1,602 centimeters squared.